Over the past videos, we covered why neural networks are capable of approximating functions, how we can learn network configurations using backpropagation, how we can use computational graphs to calculate the gradients and partial derivatives with respect to all of these networks parameters, and specifically in the last video, we took a look at stochastic gradient descent and how mini batches can help us speeding up the training and make it more stable. If you have missed out on the previous videos and want to learn about these topics, I will leave a link down in the video description for you to check out the complete neural networks from scratch playlist. So with that out of the way, we will take all of these concepts of the previous videos from the drawing board and spell them out in code. Specifically, today we will implement a simple neural network for our XOR function example, and we will do so end-to-end handcrafted just using PyTorch tensors for the matrix multiplication. So everything starting from the layer definitions as matrices of weights and biases to the forward pass to calculating the loss and calculating the partial derivatives with respect to all of the network's parameters, and eventually updating the network's parameters in order to minimize the loss. So today we will take all of the little puzzle pieces from the previous videos and take them all together such that we have an end-to-end implementation of all of these concepts. But in order to do so, we have to revisit all of these puzzle pieces again to be able to put them together. So let's start with how the neural network is structured again. So we had 2 neurons for the first layer and 1 neuron for the second layer for the final activation. That means for 2 inputs of the first layer, we need a 2x2 matrix, for the weights. So the weights of the first layer will be a 2x2 matrix of weight 1, 1, weight 1, 2, weight 2, 1, and weight 2, 2. And also we have the bias 1, bias 2 for both neurons, and they represent the parameters of layer 1. So what does it look like for layer 2? Layer 2 has 1 neuron, 1 output neuron, so that means it has 1 column. And 2 input neurons, that means it has 2 rows, so a 2 by 1 weight vector, and obviously 1 bias. So that is weight 1, weight 2, and the bias for layer 2. And this would basically be the layer definition for our neural network, all of the parameters that we need. So if you recall the last video, we said that when we take batches of input, so multiple inputs at a time, that we have to replicate the bias row-wise. So for instance, we have an input vector that has 2 inputs, x1 and x2, with all of its features. And we multiply that by the weight matrix, weight 1, 1, weight 1, 2, weight 2, 1, weight 2, 2. We said that we cannot use the single row vector b1, 1, b1, b2, but rather we have to replicate for each of the individual inputs the bias row-wise. And in theory, we would have to do so, but all of this replication is implemented inside PyTorch, such that if PyTorch sees 2 matrices that are not compatible with each other, but it knows that for this specific operation, for example, the add operation, it can make it happen by replication such that the shapes match in order to complete the operation. So in this case, if we would just hand PyTorch this X matrix and the W matrix and just the row vector B1, B2, it would be able to infer that it has to replicate B row-wise to be able to add B to the result of X times W. And this concept is called broadcasting. Okay, so we started with revisiting the neural network and how we can define the layers and its parameters as matrices of weights and biases. That we can now use to implement our layer definition inside of our implementation. Starting in Python, we want to use Torch obviously we use Torch for the matrix multiplication. You could use any other library that enables you to multiply two matrices and add them together, and that also supports broadcasting like NumPy. And for this entire thing we only need one function, that is the main function, and if we call this script as our main script, then we want to execute the main function. And inside the main function, we now want to define our two layers. So we start by saying the weights of layer 1 is equal to something, the bias of layer 1 is equal to something, and we also need the weights for layer 2 and the bias for layer 2. Okay, so now we said the weights have to be of shape 2 by 2 and the bias has to be of shape 1 by 2. How do we initialize these weights? Well, we could initialize all of the parameters by saying they're all 0, they're all 1, but in practice it turns out that initializing them in a random manner is oftentimes better. So we will do so here as well. We say this is just a random matrix, all of the values are uniform random, and now we provide a shape that is 2 by 2 for the weights, and for the bias we say that this is a 1 by 2. Okay, and for the second layer it will be a random matrix of 2 by 1 for the weights of the second layer, and a 1 by 1, a single value basically, but we're defining it as a matrix because we can then replicate them and broadcast automatically for the bias of layer 2. Okay. So this is the definition of our entire neural network, at least for the parameters. The next thing we have to cover is the forward pass. And we said the forward pass is defined by these equations. The output of layer 1 is equal to x times the weights of layer 1 plus the bias of layer 1. The activation of layer 1 is equal to the sigmoid function of the output of layer 1. The output of layer 2 is equal to the activations of layer 1 times the weights of layer 2 plus the bias of layer 2, and the activation of layer 2 is equal to the sigmoid function of the output of layer 2. I'll just fly over this because this is just repeating all of the stuff we have pointed out in the previous videos. If you missed those, you can rewatch them in the playlist. So the forward pass is the first thing we have to define inside our training loop. So if you recall, our training loop consists of a forward pass, calculating the loss, calculating all of the partial derivatives with respect to all of the network's parameters, and finally updating the network's parameters. So let's start with forward pass. We said that the output of layer 1 is equal to x times the weights of layer 1 plus the bias of layer 1. So we say O of layer 1 is equal to x, and now we want to make a matrix multiplication, which we do by this add operator, and we multiply with the weights of layer 1, and eventually we add the bias of layer 1. So now we have the output of layer 1. Next up is the activation of layer 1, and that is the sigmoid function, which is defined by 1 over 1 plus, and now we need e to the power of negative x. Torch has a function for that, that is exp, and we can provide the negative output of layer 1. This is the sigmoid function. Next up is the output of layer 2, and that is obviously equal to the output to the activation of layer 1, and then matrix multiplied with the weights of layer 2 plus the bias of layer 2. And the activation subsequently is the sigmoid function of that output, that is 1 over 1 plus torch.exponent minus O layer 2. Okay, so this is the entire forward pass. We said inside our training loop, the next step would be to calculate the loss. So let's calculate the loss. What do we need for our loss? If we revisit the loss again, we said that for our batch example where we have multiple inputs, our aggregated batch loss is defined by 1/2 and then the sum over each of the individual inputs and its outputs. And I introduce a parameter I, and then the activation of layer 2 at index I minus the y hat at index I squared. So the activation of layer 2 becomes in the batch case a vector, and this becomes a vector as well. So in this vectorized form, it would just be L is equal to 1 over 2, and then the sum over the difference between A layer 2, the vector, minus y hat squared, like that. So let's define a loss function. So the loss function is equal to 0.5, and then we have the activation of layer 2 minus the y. That is the difference. This difference we want to square, so torch.square, that is a function that torch provides. And this we want to eventually reduce to one value, so we sum all of the individual values up. The torch sum of torch.square, and then the difference between the two vectors. So as you can see, the forward pass relies on the x and the y in the end, and we haven't defined those yet. So we have to define our inputs and our outputs, and we said that our input is a matrix of the number of examples in the batch by 2. So all of the possible configurations of x, all of the possible configurations of x is 0, 0, 1, 0, 0, 1, and obviously 1, 1. Let's make it a little more readable. And the corresponding output is also a torch tensor, and we expect a 0 for the first one, we expect a 1 for the second input, we expect another 1 for the third input, and we expect a 0 for the last input. So 1, 1 should be 0, 0, 0 should be 0, 1, 0, and 0, 1 should be 1. That is exactly that. So we have to find our inputs and the corresponding outputs that we would expect. This, of course, would be some kind of data set you have. And in reality, of course, you would define the batches not as the entire data set, but rather a small subset. But in this case, we will just pass the entire data set we have at hand at a time, at each iteration. So next up would be the backward pass. So all of the partial derivatives with respect to the network's parameters. And I will not repeat all of the individual calculations which were necessary to come up with all of the partial derivatives. I will just write them down here again. If you want to know how we came up with those, then you can check out the video where we derived those. So of course, first we have to calculate the loss with respect to the activations of layer 2. And that we said is the activations of layer 2 minus the desired output. Then we would have to calculate the derivative of the loss with respect to the output of layer 2. And that is equal to the derivative of the loss with respect to the activation of the layer 2 by the chain rule times the activation of layer 2 times 1 minus the activation of layer 2. Then next up is the DL, the weights of layer 2, and that is equal to the input of layer 2, that is the activation of layer 2 transposed times the derivative of the loss with respect to the output of layer 2. Then we also need the derivative of the loss with respect to the bias of layer 2. There we said this is the column-wise sum of the derivative of the loss with respect to the output of layer 2. Then we also need the derivative of the loss with respect to the activations of layer 1. There we said this is equal to the derivative of the loss with respect to the output of layer 2 times the weights of layer 2 transposed. So this is the backward propagation for the second layer. Let's implement that. And we denote that by adding a d as a prefix. So dAL2 is equal to AL2 minus y. dOL2 is equal to dAL2 by the formula times 1 times AL2 times 1 minus AL2. Then the derivative of the loss with respect to the weights of layer 2 is equal to the activation of layer 1 times the derivative of the loss with respect to the outputs of layer 2, and then transposed with the dot t, we can transpose a torch tensor. Then we also have to come up with the derivative of the loss with respect to the bias of layer 2. That is equal to the column-wise sum we set. So the column-wise sum of the outputs of layer 2 the derivative of the loss. And here we can basically sum in two different ways, either in row or in column direction. And we want to do so in column dimension, and that would be dimension 0. So that is the meaning of the 0 that we do it column wise. So next up is the derivative of the loss with respect to the activations of layer 1, which we need to in turn calculate the partial derivatives of the loss with respect to all of the network's parameters of layer 1. And that is the output of the derivative of the loss with respect to the output of layer 2 times the weights of layer 2 transposed. So this is just copy pasting all of the formulas, and basically the same thing applies for the first layer as well. So we can just decrement all of the suffixes of the L by 1, and would just be the same, except for the case where we don't have to calculate the derivative of the loss with respect to the actual inputs of the network, that we can omit. So we know that the derivative of the loss with respect to the output of layer 1 is now defined. We previously defined it here, but now we use the derivative of the loss with respect to the output, or to the activation of layer 1 multiplied with the activation of layer 1 multiplied with 1 minus the activation of layer 1. It's basically the same thing as in the second layer. Now the derivative of the loss with respect to the weights of layer 1, that is the x, the input of the layer, times the derivative of the loss with respect to the output of layer 1 transposed. The derivative for the bias is equal to the torch.sum do L1, and also column wise d and dx we don't need. First layer, second layer, and that is it. So now that we have that, all of that's left is updating all of the weights and biases using the individual partial derivatives we have calculated here. And if you recall from the previous videos, we don't just subtract the gradient we have calculated right now. We do so by introducing a learning rate. So we introduce a hyperparameter that determines how far we travel in the parameter space alongside the gradient to update the individual parameters. That is a hyperparameter. That means we can change it to our desires, and different learning rates for different problems can drastically change the outcome of the training. So we want to update our weights and biases. So the update will look something like this. We have obviously the negative gradient, so a minus sign, and then we introduce the hyperparameter eta. So the learning rate is often denoted as eta. And obviously we also need the gradient of the loss. So let's implement that update. For each of the individual parameters we have to perform this update. So that is WL1 is now minus equal the eta times the DWL1, then the bias of layer 1 and minus equals eta times the DBL1, the weights of layer 2 minus equals eta times the weights of layer 2, and the bias of layer 2 minus equals eta times the D bias of layer 2. And of course, in the beginning, we have to also define eta. So we said that all of these individual steps are part of the training loop, and at the moment we don't have a loop, so let's change that as well. Obviously the layer definition is not part of the loop, but the forward pass, the loss calculation, and the update are part of that. So we introduce a for loop for I in range, and then we can also define a parameter that we call epochs, and we say epochs equal to 1000. So we have 1000 epochs for now. And all of these things will now go into the loop. And for the sake of visualizing the progress we made inside the training loop, we also want to store the individual losses of the epochs. So we need a list that can fit all of the losses of the epochs. That is, we can have a loss history tensor, and that is a torch tensor of size epochs. And let's say it's also the D type is also torch.float. And of course, in each iteration, we now want to set the loss history at the index I to the loss. And we want to plot that loss, so a quick matplotlib import, matplotlib, pyplot, spt. And in the very end, we say plt.plot loss history. That won't be very, so that plot won't be very nice, and but for the sake of visualizing just the progress, it will be fine. I promise you. So let's revisit that. We have to find our input, we have to find the desired output, we have to find our network as weight matrices and bias vectors. We have a loss history, and then we defined epochs, so the number of iterations we have to go through. We have a forward pass, we calculate the loss, we do all of the partial derivative calculations, and in the end, we update all of the weights and biases. And we add one more thing. We tell Torch to not keep track of the gradients on its own. If you recall the computational graph video, I mentioned that these frameworks like Torch and TensorFlow are capable of building these computational graphs on the fly and use them to calculate the gradient on its own in an automatic way. And because we do that all by hand here, we don't need them. So that would just be extra work the processor has to do, and we can omit that because we do it manually. So we made one mistake. This is not a tensor of one value. This is a tensor that we can define as initially zeros, so torch.zeros, and this is now the size. Okay, so we made one mistake here. It has to be this one transposed. If you recall this, I made it correct here, but in the implementation I had it the wrong way around. So we have to change that as well. It's the input transposed. And we also have to make this a matrix multiplication. And we can run this now. And we will get something like that. So that's great. You can see that in the beginning we had a loss that's quite high. It went down to 0.5 and it was stuck at 0.5 for quite some time, but in the end was able to find the optimum and retrieve a loss of 0.027 or something like that. And if you recall the XOR function, you see that this makes some sense because the XOR function has a local optimum when it's just disregarding the input and predicting 0.5 no matter what. And that is what's happening here at this loss of 0.5. It's just predicting 0.5 all the time. It's finding this shortcut, but eventually we manage to get the optimal configuration at this later stage. If we would now, for instance, increase the learning rate to 0.8, then we would see, okay, let's run this again. Then we see we reach that minimum a lot faster. But that is the case for this specific problem where we have very clean data. So our data is perfect. There's no noise in our data. If you have noisy data, then using high learning rates might not be a very good idea. But in this case, we profit from learning rates that are high to overcome this local optimum at the loss of 0.5. What if we don't do this entire batch loss, but rather pass in single values at a time? So we said in the last video that we use an aggregated loss, a batch loss, to stabilize and speed up the training, but now we want to see that in action. So in order to do so, we now need an inner loop that goes over all of the inputs, the amount of inputs we have inside our batch, and then we have to perform a reshape to keep the dimensionality such that the matrix multiplications still work out. And We do that for the x, for the y, and basically the other things are the same. The loss is now a little bit different. We have to keep a running loss for each epoch, and that is we have to sum the loss together. So for each epoch, we iterate over all of the inputs, and we accumulate the loss, and in the end, we divide by the amount of inputs we have per batch. So that is basically averaging out the loss. So to demonstrate how the learning rate affects the final result, we can reduce the learning rate now to 0.1. And we see that in this case, we reach the minimum a lot faster, but it's not, the minimum was better the last time. Now it's at 0.12, so we got stuck at some local optimum here, of course. If we increase it again to something like 0.9, and then we redo that, we see that we can find something that's even better at 0.09. But we are also, again, we were stuck in this local optimum. We were stuck, but eventually we got something that was even better in this case. And if we, for comparison, use the batching again, we just comment out these lines. So if we do that for the batch case, in the end it doesn't make a huge difference. But in this batch case, you see that it takes us a lot more time to get out of this local minimum here and here to reach something that is close to optimal. And this might also be due to the fact that we provide the entire data set at a time. And what you were able to see in this example as well was that in the batch case where we provide the entire data set at a time, we got stuck at the local optimum at a loss of 0.5. And in the case where we provided the examples individually, we didn't get stuck at that local optimum. And this aligns with what we said in the last video, where we stated that using batches might cause convergence to a local optimum, while providing individual examples might lead to a better optimum. So there is a difference in convergence behavior. So what I want you to take away from this is that choosing batch sizes and choosing learning rates and all of the other hyperparameters that are introduced by other methods does matter, and maybe leads to different outcomes, and maybe even drastically different outcomes. So in this video, we saw how we can implement a neural network from scratch using just a library that enables us to do basic matrix operations. So we saw how all the puzzle pieces came together and formed an entire picture that we can use now as a tool to approximate functions. So we looked at differences between batching and non-batching. And in this case, where we had perfect data, we don't really need this aggregation of the loss. But in cases where we have noise in the data, it might be very, very useful. We saw how different learning rates can affect the progress we can make inside the training loop, and that choosing a learning rate is obviously problem specific. In the next video, we will take a closer look at the update of the weights again. In this case, we just multiplied the negative gradient with a learning rate, but there are more advanced methods that enable us to reach the minimum even faster, such that we can accelerate the training process. So if you don't want to miss out on the future videos, consider subscribing, leave a like and a comment if you want, and I will see you in the next one. Bye.